I welcome you all to this round of lecture annotation video. So in this lecture we will discuss about how are we processing or executing different types of operations, arithmetic operations. For example, right here we have how we design the arithmetic units to perform addition, subtraction, multiplication and division. We are already kind of familiar with addition and subtraction. We will actually focus on multiplication and division portion of this arithmetic operations. So all arithmetic functions can be approximated. So what do we mean by approximated is that we kind of guess a close value and then get calculated and then perform the calculation to get closer or more accurate than the approximated value. And here we will focus on how we determine how the arithmetic logic unit actually performs the calculations, and floating point and pipeline processing. This is a very important topic. I have told you before that pipeline is just we're just a start, and we will see it frequently in the future. So this is another just instance of me being right. So let's move on forward. So using the binary addition format, what do we see here is that when we add these numbers, the result when we add these two bits, we get a single digit, two digit of 3 and 4, we add them to get 7, and when we add 8 and 9, we get 7 with overflow of 10, that is we actually get 17, and this 10 plus 7, 10 is the overflow, that we require two digits or two bits to represent 17. So it is called an overflow or carry in our computer science terms. So we are already familiar with these things, how half adder works. It adds two digits and gives us the result. And when two digits are added like this, and that both value, we if we add 1 plus 1, we get 2 in decimal format, and 1 0 in the binary format. So 0 is only counted in the half adder, but full adder just gives us this 1 and 0. This is what happens in here. And what also happens in the other example is that it performs, it takes input from another source, and with it we call it a carry input, which can also be a 1 or 0. Basically all the inputs that can be possible for any variable or inputs 1 and 0. So this is what happens when we get also a C in, carry input 1, and then we have the result 1 and 1, that is 1 plus 1 plus 1, we get 3 in decimal, and when we transform it into binary, we get 1 1 in binary. So this is what happens. So first digit is our result, and the other digit is our carry output from these operations. So this is what happens while we are executing addition operation. I think you get that. It is already discussed in the previous lectures. So this is the actual format, the truth table. This is the mathematical input and output, and we get two inputs, x and y, two variables. We are going to add and output it in the sum. It is the half adder version or implementation. So when we get the value of sum as 1, that is the result is 1, what happens here is that we are taking the input in x as 0 and taking input 1 in y. So it's represented by like this, x prime or x bar, what you are familiar with, and then we add for when we input 1 in x and 1 in x but 0 in y, we get another value 1 for the sum. So in expressing in the algebraic format, we get this expression at the end, that it actually corresponds, or it's similar with the operation of XOR. That is what happens right here. I think you get that. It's very familiar with you. So what happens in here? So let me first tell you, this input is kind of overflown to the output. So when we have three inputs and consider a carry input and extra input, which can be both 1 and 0, what happens then? So when we add these values, we get all zeros. So the result is the sum, and the carry output is also 0, and so on. So I have already told you about this. So this is the result, carry and sum is both 1. So this is all about the full adder truth table. So I think that you are quite familiar with this. So let's move on forward. So this is the ripple carry adder, etc. I have already shown you in the mid topics. So I'm not going to repeat these things. But if you want to see some elaboration, please follow my previous lectures, or you can go through in the internet. So what happens in the carry look ahead addition is that when we are sure that these bits might generate a carry, we are expressing it already in the carry. So this is what happens right here, and carry is generated regardless of the values of other carry values. And so I'm going to leave it as self-study. Use your digital electronic books for this topic, the famous book of Maurice Mano, and I think you would get that it's not so important in computer architecture course, so I'm going to skip it for now. So let's move on forward. Now what do we have here? What we have here is how we can do the perform the multiplication operation using the hardware. We are getting to know the process very soon. So there are two types of multiplier available. One is combinational multiplier and another is sequential multiplier. So what are the characteristics of combinational multiplier? It uses an array to carry save adder, that is it performs a addition operation, then it saves in a memory, and then it goes on to perform another addition with the partial results. And these are the procedure how a combinational multiplier works actually. But there are trade-offs with space and time. If we can use a complicated hardware, so that it supports, say for example, 8 bits of calculation, it would need much space when we design a multiplier of 4 bits. So this is all about the combinational multiplier. And when we go through the topic of sequential multiplier, what it does is that it executes a sequence of add and shift operations, and it tries to minimize the number of add and shifts required. The advantage and disadvantage is that the advantage is basically the existing registers and LUs can be used in the sequential multiplier. We don't need another extra kind of hardware or capabilities. But the disadvantage is that it is very slower. It is very slow compared to the combinational multiplier. So these are the topics of the sequential multiplier. So let's move on to the process. So what are we seeing here right now is that when we consider the case of decimal multiplier, what we are doing is that we are multiplying 156, the multiplicand, with this digit first, and we get this result, and then we multiply this 0 after shifting a bit to the left, and then we multiply this multiplier bit with digit with the multiplicand, and we get the value 0, and then we use this bit and multiply the multiplicand, all the while shifting another to the left, another bit to the left, and then we add these total digits at their position, and we get the final product. So similar kind of result always takes place in this. So this is 1, 2, 4, 8, 16. So this is 26 multiplied by 23, and we get this kind of huge binary result. So what happens here is that this digit 1 is multiplying with this multiplicand 0111010, which is 26, and we get this 26 right here, and then we go on to the next bit and multiply the multiplicand with that, and also left shifting the result, we get this value, the result, and so on. This thing continues, and at the end we use addition and find the result or the product as shown here. This is what happens when we try to multiplication operation in binary number system. So I hope you get that. So let's move on forward. These are the observations right here. The multiplication of single digits in binary multiplication is just an AND operation. So single digit is what? Why do we call this just an AND operation? It is because like this. So we were representing 0, 1, 0, 1, 1, 0, the previous number that we have gone through. So what happens here is that when we multiply it by, say for example, 1, we are performing an AND operation with every bit of the multiplicand. So when we say for example 0, 1, 1, 0, 1, 0 is multiplied by a bit 1, we are considering the result is that every bit is performing an AND operation with this bit. The multiplicand's every bit is considering to have a AND operation, performing an AND operation, and we are getting the result. So that's why this is called the AND operation that we are performing right here. And the multiplication of two n-bit numbers can be accomplished with n-1 additions. So these are the observations that we get from this. Now, how this AND operations and additions are performed, we can use an array of AND gates and half adders and full adders to perform this operation. So this is how we get to multiply two binary numbers. Now, in your next class, I will focus on the sequential multiplication, and which uses one parallel adder and a set of registers capable of shifting and control logic, and use the ASM design, algorithmic state machine design, that you are familiar with, to design this circuit. The multiplier recoding can be used to reduce the number of adds and subtracts required. That is, it can be reduced and be more easier. Then we can very much imagine how easy the process can be. And this processes Booth's algorithms and Booth's multiplier and modify Booth's algorithm. We will see it in the next class. So it looks like kind of this multiplication. We have to go through the cases first. We have to analyze the cases. Multiplication, how we can do them with sign numbers, and then so on. So it's all for this lecture annotation video. I hope you get that. See you in next lecture annotation video. I hope it would be easier. And if you have any problems, please share with me when we resume in the Google Meet. Thank you all.